Let us embark on an imaginary journey from the top of Mount Wilson to the farthest reaches of the known universe. Traveling at the speed of light, 186,000 miles per second, how long would this journey take? Albert Einstein demonstrated that time would be dramatically altered for anyone traveling at such a speed. But for the sake of simplicity, we'll set aside this effect by measuring time with earthbound clocks. We depart Mount Wilson on January 1st. Hurtling through space, we quickly pass the orbit of Mars in just 4 minutes, 30 seconds. We continue on, past Jupiter and the other gas giant planets, Saturn, Uranus, and Neptune. And 5 hours and 30 minutes after leaving the Earth, we fly past Pluto and its companion moon. Our journey has taken us more than 3.5 billion miles to the outer limits of our solar system. And back at Mount Wilson, it's still January 1st. We now take our first steps into interstellar space. Behind us, our neighboring planets and the Sun quickly disappear from view. The void of space is broken only by the glimmer of stars so distant they do not yet appear to move, even though we continue to travel at the speed of light. A year passes, then 2 years, 3, 4 years. Finally, on April 19th of the 5th year, we reach the Alpha Centauri system, the nearest stars to our Sun. We have traveled nearly 25 trillion miles, yet our journey has barely begun. We are now 10 light years from the Sun, far enough out in space that the stars within our galaxy appear to converge. 100 light years from the Sun, patterns of gas and dust from an arm of the Milky Way galaxy surround us. 1,000 light years. The galaxy's arms and central disk become more defined. Yet it is not until we've traveled at the speed of light for 100,000 years that the entire spiral shape of the Milky Way is recognizable. From here on, each point of light we see is no longer an individual star, but an entire galaxy composed of billions of stars. 5 million years after beginning our journey, the Milky Way is recognized as part of a cluster of at least 30 galaxies, known as the Local Group. Bound together by gravity, the galaxies that comprise the Local Group span a region of space more than 3 million light years across. "50 million light years out, we encounter the large Virgo cluster, containing more than 2,000 galaxies. And so it goes, as we continue to travel deeper into the cosmos. We pass cluster after galactic cluster, each a building block of a far greater framework. 1 billion years pass. 5 billion. 10 billion. Finally, after 14 billion years, we are able to discern the large-scale structure of the entire universe. At least 100 billion galaxies stretch in thread-like chains across the cosmos, forming a tapestry of unimaginable dimensions.
The universe is extraordinarily rich, extraordinarily vast. The number of stars that we can see, it's on the order of 10,000 billion star systems. So unless there's something very, very special, miraculous, if you will, about our solar system, about our planet Earth, unless there's something extraordinarily unusual about it, then what happened here must have happened many times in the history of the universe.
In my early years, I came to believe very strongly that there must be other civilizations out there and that the galaxy was teeming with life. And so I was a strong supporter of the search for extraterrestrial intelligence. My belief wasn't based on any real hardcore scientific arguments. It was just the impression that I had that the galaxy was such a big place. And I didn't give the other side of the equation much thought. In other words, there's two sides of the equation. There's the number of stars, the number of trials, if you will. But the other side is the factors. It takes a lot of factors to have a habitable planet and a planetary system.
For Gonzalez and other astrobiologists, these factors, required for the Earth's habitability, became the focus of extensive research.
We've demonstrated in dozens of different ways the laws of physics and chemistry that pertain in a laboratory anywhere on Earth apply anywhere in the solar system, apply anywhere in the galaxy, and in many cases out to the most distant galaxies that we can see.
There are indeed unchanging physical laws in the universe that apply to the entirety of the universe, that they're not localized to one place.
This consistency in the laws of physics and chemistry has led many researchers to conclude that the factors necessary for complex life on Earth are also the best parameters in the search for habitable planets elsewhere in the universe. Most serious discussions about these factors begin with the same prerequisite: liquid water.
All the searches that are being done for life elsewhere, their starting position is a terrestrial class planet with water.
It is now widely recognized that the chemical properties of water are exquisitely suited for carbon-based life. These properties include water's ability to dissolve and transport the chemical nutrients vital to all living organisms, and its unmatched capacity to absorb heat from the sun, a process critical for regulating the Earth's surface temperature. In liquid form, water is an extraordinary substance, and its existence hinges upon another factor essential to complex life: a planet's distance from its home star.
It's like what they say in real estate: location, location, location. A habitable planet lives in what we call the Goldilocks zone. It's not too hot, it's not too cold, it's just right. And when I say just right, I mean just right for water.
Liquid water really helps define the habitable zone. If it's too hot, again, the water just boils away. You just can't get condensed water. It's too cold, as in Mars today, it freezes out.
Within our solar system, the habitable zone is relatively narrow, beginning well outside the orbit of Venus and ending short of the orbit of Mars. If the Earth were just 5% closer to the Sun, it would be subject to the same fate as Venus: a runaway greenhouse effect with temperatures rising to nearly 900 degrees Fahrenheit. Conversely, if the Earth were 20% farther from its home star, carbon dioxide clouds would form in its upper atmosphere, initiating the cycle of ice and cold that has sterilized Mars.
The presence of liquid water is a necessary condition for life, but it's not a sufficient condition. After all, there may be liquid water under the frozen surfaces of Mars and Jupiter's moon Europa, but there's very little chance that complex life exists in either of these places. You see, contrary to what the Copernican principle might suggest, the recipe for life is much more complex than just add water.
If a recipe for a planet capable of supporting complex life really did exist, then what ingredients beyond liquid water might be required? The list of necessary factors continues to grow.
We live on this paper-thin crust. If the Earth's crust were significantly thicker, then plate tectonic recycling could not take place.